Can you power an IoT sensor from ambient RF energy? Is it viable for a commercial application? In this video, we'll explore the concepts of RF energy harvesting and showcase the EP's 2.4 GHz RF energy harvesting evaluation board. Hi, I'm Robert Huntley, electronics engineer, technical writer, and founder of 7400 Technical Marketing. You'll find the links to the resources and a copy of the slides in the notes section. We're all familiar with large-scale energy harvesting using solar panels and wind turbines. But how about microscale energy harvesting for a low-power sensor? This is where the power budget is measured in milliwatts, not megawatts. There are many ways this power can be realized, vibration and solar being the most practical for space-constrained edge node sensors. But what about harvesting ambient RF energy? There's been a lot of interest in this recently, so join me in finding out if it might actually work. To start with, let's think about what we know about the RF energy around us. It broadly falls into three types: intentional, anticipated, and unknown. Intentional relates to RF energy that is purposely directed to devices to supply it with power. More about that later. The anticipated includes our cell phones, transmitters in the local area, and the Wi-Fi router in our homes. Basically, these are sources we already know about. There are many unknown sources. That could be a CB radio enthusiast next door, a Wi-Fi doorbell, a host of wireless devices in the surrounding homes and offices. But before we see if RF energy harvesting is viable, let's review some of the terminology we'll be using. In the resources folder for this video, I'll put links to some useful websites where you can learn more about things like free space, path loss, and antenna gain. We'll also be using dBm as the primary measure of RF energy. 0 dBm equates to 1 milliwatt of RF energy and can also be expressed in terms of voltage with respect to a 50 ohm matching impedance. Free space path loss relates to the amount of energy lost in the ether between what is emitted from the transmitter and received at the receiver. Free space assumes nothing is in between. But in our homes, we know things like walls, particularly stone or brick, they reduce the signal. Path loss is expressed in dB and can become a significant consideration in working out what you need. Antennas that exhibit a gain compared to an isotropic radiator serve to increase the transmitter output, and likewise the received signal. If your router has small antennas sticking out the back, these typically have a 4 dBi gain. The focus of attention in this video is the frequency of 2.4 GHz used for Wi-Fi. An average home router output is about 20 dBm. Between the router and our device, say a laptop, it experiences path losses. Generally speaking, a Wi-Fi module in a laptop would require minus 30 dBm for an excellent link reliability and quality of service. That equates to a path loss of about 50 dB or less. Once you get to minus 60 dBm or below, that's a path loss of 80 dB. Link reliability and quality becomes marginal. Now, one aspect of harvesting an RF energy signal we've not mentioned yet is the type of signal that would be the most desirable. What does the wireless signals around us look like? Would our router give a suitable signal? Or is a more suitable and specifically designed wireless source required? Of course, we already know the answer to this from our knowledge of solar and wind turbines. Yeah, a constant supply of wind or strong sunshine works best. So let's see what the 2.4 GHz spectrum looks like around my lab. You'll see occasional bursts from my laptop and home router on the right of the display, the highest burst reaching minus 30 dBm. Compare that against a continuous carrier wave signal providing a constant minus 30 dBm signal. We'd be unlikely to harvest enough energy based on a bursty signal that comes out of our Wi-Fi router. So before we take a look at the board, I just wanted to point out a couple things on this diagram. The evaluation board has actually two RF inputs. There's one for low level and there's one for higher levels. The low level input accepts anything from minus 22 dBm up to minus 10 dBm input. And the high level is anything less than plus 20 dBm. The board datasheet states a code start of the PMIC from anything above minus 18 dBm. Now let's take a look at the board itself. At the top we've got the two SMA connectors, which has got the low and the high input, and beneath them there's a dip header for selecting between the two. Then we've got the storage element. I'm using a supercapacitor there, and on the high voltage output I've got a simple 10k ohm resistor as the load. That's the PMIC itself, and then at the bottom here is the configuration headers for deciding which storage element you're using. This is a simplified version of an application circuit. Everything in the shaded grey box is basically on the evaluation board. And then the two elements here, we've got the storage element, which I've already pointed out I'm using a supercapacitor, and then the actual application circuit that you're using, and the selection between the high voltage and the low voltage outputs. EPs provide an application note that provides this configuration information. It's basically the dip header which I pointed out at the bottom of the board. And the arrow shows the configuration I'm using, which is a single cell supercapacitor, and shows that the voltage ranges and the LDO output voltages of the PMIC. In my test setup, I've got a 2.4 gigahertz signal source, which is directly connected into the high input on the evaluation board, and I've got the output set at plus 15 dBm. I don't have a high enough power emitter that I can use an antenna, otherwise I would have. And then there's the supercapacitor and a constant load on the high voltage output provided by a 10k ohm resistor. So here we are in the lab, and we've got the board set up here, the evaluation board with the supercapacitor on the right hand side there, and the load just in view. Currently I've got 2 meters attached, 2 DMMs attached to this. The lower one is showing the voltage across the supercapacitor. Let's just change the zoom a little bit there we go. That's the voltage across the supercapacitor on the bottom one, and on the top one is the load output. That's the high voltage output, 1.82 volts. Now currently I'm not feeding it with any energy, so the supercapacitor is actually discharging without any input, and it will reach a point where it will cut off the output to protect the application circuit. Okay, so let's turn on the signal, and I'm using my signal generator here with an output of plus 15 dBm, and that's feeding into my spectrum analyzer here. The output's currently off, remember, so there's nothing showing, and that's just teed off. I've got 2 attenuators in circuit, one external, that's a 20 dB attenuator on the external, and there's a 20 dB attenuator on the inside too. And there, that's feeding down into the evaluation board, where it's going into the high input range. Okay, so let's now turn on the output, and you'll see on the spectrum analyzer we've got an output showing now, which is coming up at minus 26 dBm. So there's a few, it should be minus 25 dBm, but we've got a few lossy T-junction there, and in the length of the cable as well. Now if I just come across to the DMMs here, you'll notice that the top one has turned off. That's isolated the application circuit because the supercapacitor has dropped below the particular point of I think it's about 2.18 volts, and it will start to now charge up until it reaches 2.27. Okay, so here we are back again, and the storage element, the supercapacitor, has gone past the point that the PMIC will turn on, bring on the high voltage output, and you'll see the top DMM there showing 1.8 volts. Now this is again just to show, this is sending out my signal generators plus 15 dBm, and on the spectrum analyzer we've got minus 26 dBm roughly showing, and that's the board. Now what we can do is actually show it working on the low input, so I'm just going to make those changes, turn off the output, changing it across to the low input. There we go. Now we've got to bring down the output from the signal generator. And bring that down to minus 8 dBm. There we go. That should be set up. You'll notice all the time that the output voltage is being maintained, 1.8 volts, although the storage element is discharging. So now I'm going to turn on the output again. Oh, one thing I didn't do is to change the dip header. There we go. So output on. There we go, that's down to minus 37 dBm. And in this instance the output voltage has been maintained, but you'll see that the voltage across the storage element is slowly reducing, and it will get to the point where the output will turn off. Probably my 10k ohm resistor as a load, it's a constant load, so it's not really representative. To do this in a real life application, of course we're going to have perhaps if it's an IoT sensor, then it will come on. Once the sensor is activated, it's going to transmit data every so often, read the sensor, transmit that information, and then go back to sleep. So obviously the next stage of doing this would be to get the circuit, prototype it, the sensor circuit, prototype it, check it out for its power profile on using a device like a Publitek OT, and then that gives us a much better idea of what's required for the storage element that we might want to use.
So is RF energy harvesting viable? Well, yes it is. Certainly not reliant on bursty signals like Wi-Fi, but a direct RF energy source coming from a proper emitter designed for the purpose. In so taking that route, you've got to think about what's the path loss, how you're going to architect the RF side from the emitter antennas that you're going to use, and you need to do free space path loss calculation to do that, which we'll come on to. Understand your application's power profile and the duty cycle. Again, that's a very, very important aspect of this. Some applications may suit energy harvesting more than others. And for that, you need a good awareness of your active and sleep power consumption profiles. And certainly a good tool which I use is the Publitek OT power profiler for that ideal. And then your other decision is really relating to should you use a rechargeable battery or, as I've done in this case, a supercapacitor. So working backwards from what you need in terms of an RF source to make this work, the path loss calculation, as I mentioned, is important. In this example, using the calculator, again, I'll provide the link for this, path loss over a distance of 3 meters, operating at 2.4 gigahertz. I'm assuming the transmitter, the emitter, actually has a 6 dBi gain, and the receiver aerial, slightly smaller aerial, that's got a 4 dB gain. And that result of that calculation ends up with a path loss of about 40 dB. So working backwards from that and assuming that you've got and you require a minus 15 dBm input, that would require an output of from the emitter of plus 25 dBm. And that's certainly in line with many of the commercial emitters that you can get on the market from various sources that are providing 3 watts, which is equivalent to 34 dBm output. Another consideration is, does it really suit your application? There's a number of issues here, certainly relating to cost. You've got the cost of the emitter and the antennas to think about, provisioning power to the emitter as well, and the through-life cost during ownership and operation. The other aspect of this is that it's not particularly power efficient, because obviously you're having to power the emitter, and you've got power losses in getting the signal across, or the energy across to the receiver for that. But for a single sensor, I don't think that that's perhaps viable. For many other applications, example of retail tags, then obviously you're feeding from the emitter quite a large number of potential retail tags, and that would be a very efficient way of doing things. So that's it. I hope you've enjoyed this video. It was certainly interesting putting this together and evaluating the board. Please smash the like button if this has been helpful for you, and let me know in the comments if you end up making a RF energy harvesting based on the information presented.